So the distillation process we see here is what we were supposed to be trying to do here, which was to boil off the water, and it comes off as fresh water, leaving the salt behind. Then it condenses, and then it precipitates out as fresh water. On page 112, it tells us that the residence time, your residence is where you live, right? Right? The residence time is how long the water lives in any one place. That makes sense, doesn't it? So you see here they give averages, and they said very clearly that these are just averages. We don't know if these are perfect by any stretch of the imagination. But the water is the longest in the ocean. 4,000 years it can be in the ocean. Some water's been in there since probably right after the flood. You know what I'm saying? It's never gotten out since because it's down deep in the ocean somewhere, so it's not getting a chance to evaporate or whatever. That's a long time. Glaciers and icebergs, usually about 1,000 years. Groundwater, it could stay in there 1,000 years, but it could be as little as 2 weeks. And here in Florida, the groundwater moves very, very rapidly, so it wouldn't stay very long. Soil moisture, 2 weeks to a year. Low residence time, right? Quickly moves through the soil, whether it be transpiring out, going into the groundwater and moving that way quickly. Atmosphere, 10 days. Woohoo, it's not staying up there long, is it? It's going to come down in some form. Lakes could be 10 years. It just depends on the size of the lake and how the water moves out of it. Rivers, usually 2 weeks because they're moving pretty quickly. Swamps from 1 to 10 years, depending on how the flow is in the swamp. And so these are, you do not have to know that. You just need to know that a residence time is how long the water is in any particular source. So on page 113, 5.1, suppose you are given a sample of water taken from somewhere in the Earth's hydrosphere. A, would it most likely be salt water or fresh? Salt water. You got a whole lot more salt water than fresh. B, if it is fresh water, where did it most likely come from? Glaciers and icebergs. Thank you. And if the person who collected the sample tells you the fresh water was originally a liquid source, where is it probably from? Groundwater. Very good. I just want to see what's here next. Okay, we already talked about that. There's your distillation. Okay, that's an old style type of distillation there. Okay, we're back to that. Residence time, how long it stays in one place. Okay, 5.2, water that was originally in a plant ends up in a cloud. What two processes of the hydrologic cycle caused it to be transferred in that way? Somebody tell me, what two things did it have to go through? Yes, sir. Evaporation and, well, in this case it would be transpiration, good. And condensation, very good. 5.3, rain that hits the land can travel as a liquid into a lake, river, stream, or ocean in two different ways. What are they? Go ahead.
A stream or a river.
Okay, so that would be surface runoff. Anything on the top is considered surface runoff, so river, streams, and groundwater. So if it's on the top, just call it surface runoff. That would include all your top water. And then if it's under the ground, we're going to call it groundwater. 5.4, suppose that a scientist studies two groundwater sources. The first is an underground river that flows quickly into a large lake. The second is a large basin of underground water that moves at a much slower rate towards a small pond. Which groundwater source has the longest residence time? The second one, the one that's not moving very quickly. Thank you. Okay, and then it mentions here in the book of Job, which I don't know if you realize this, but outside of the beginning of Genesis, Job is considered the oldest book in the Bible. Did you guys know that? It like fits in there right after the flood and before Israel, Jacob. Okay, so Job is considered, outside of Genesis, the oldest book in the Bible. And yet we see that it's got the water cycle here. It's got the hydrologic cycle described in here. And then in Ecclesiastes, we also see it, which was written by Solomon. We also see the hydrologic cycle being spelled out for us. So it's interesting that it has these scientific acknowledgments. Once again, we know that God took care of it, and that's why. So let's go to the ocean and look at the salinity in the ocean. And I'm trying to remember. There's the ocean. Okay. On page 114, it talks about salinity being the amount of salt that's found in anything. And in the ocean, it's mostly water, but then it's got about 3.5% salt. And of that salt, the vast majority of that salt is what we consider table salt, sodium chloride. But there are other salts in there too, like magnesium sulfate and magnesium sulfate, calcium sulfate, potassium sulfate. There are other salts that are in there. That's that little other salts. And then 2.7% is sodium chloride, which we think of as table salt. Now, the ocean in general is 35 grams per 1,000 grams, or 35 grams per kilogram. And so that you have some idea what that's talking about, a gram is how much a $1 bill weighs. The mass of a $1 bill is a gram. So you'd have 35 $1 bills, that much salt, and a kilogram is a half a pound. Okay? So $35 bills and a half a pound of water. Does that give you a little better picture? I don't know about you, if you just say the words otherwise, I'd just go, just don't get it. So anyway, that's the average in the ocean. Now, I'm going to tell you right now, if you taste the water here in the Gulf of Mexico and you taste the water in the east coast of Florida, much saltier on the east coast. How many of you have ever noticed that? How many of you have ever been swimming on the east coast of Florida? Okay, you didn't notice that it was saltier? Taste the water next time. When it hits you in the mouth, taste the water. Water over here, much less salt than the water over there. Why? Well, there's this thing called the Mississippi River dumping into the Gulf of Mexico, putting a whole bunch of fresh water in it. We have more first magnitude springs than any place on the planet, which are springs that pump out huge amounts of fresh water. And a bunch of them are actually not only on the Gulf Coast, but they're inland in Florida dumping the water into the Gulf Coast. We got so much fresh water being dumped into the Gulf, it's not even funny. So it's a lot lower salinity in the Gulf than we do in the actual Atlantic Ocean. And some of you have tasted that. Okay, so this is an average. It depends on where you are. If you are near the outflow of a river, you're going to have fresher water in the ocean for a time than you would someplace that there is no river. Now, the salt comes from the rocks, the little minerals that are picked up by the water as it flows through the rocks. So it's little pieces of rocks and sand and stuff like that. And so that is being carried by freshwater sources, rivers, creeks, etc. It's being carried by freshwater sources out to the Gulf or out to the ocean. So like I just said, we have a whole bunch of fresh water being dumped into the Gulf of Mexico, but there's still minerals and stuff in it because that water is coming from the land and it has picked up little pieces, and as it picks up those little pieces, they get concentrated in the Earth's oceans, and therefore it turns into a salty situation and it gets saltier and saltier. And listen closely, because this is going to come up in the next half of this chapter too. Any time that the only way water can get out of a water source is through evaporation, it will be a salt water source. Anytime the only way the water can leave a source in the hydrologic cycle is through evaporation, that source will be a salt water source. Because as the water pours in, it's got a certain amount of minerals in it. And if the only way it can get out is through evaporation, it leaves the salt behind. And so eventually, if that's the only way the water can get out, it's going to be a very salty source. And that is the case with the oceans. Now, it tells us, too, that there's a certain amount of minerals and stuff that are added from volcanoes. Those silly volcanoes, they keep getting involved, don't they? We're told that if you figure out how much salt there is in the Earth's oceans and how much is being added and then how much is leaving, that the salt in the ocean is good evidence that the Earth can't be billions of years old, because if the Earth were billions of years old, then the salt is missing that should be in the oceans. They're not salty enough. And so it tells us that the top end would be 62 million years. And 62 million years, if the Earth's ocean started fresh, and then the salt has been added at the rate it is now, in 62 million years, we'd have gotten the salt content we do now. And I want you to understand, I believe the Earth is 6,000 years old. But 62 million years, let's say for an evolutionist, is not enough time, because they say the Earth is 4.5 billion years old. And so that would be not nearly enough salt. So like, who sucked all the salt out of the ocean?
Salt monster.
Yeah, the salt monster from Star Trek, actually. Anyway, okay, so there's a problem there if you're an evolutionist. The salt in the ocean tells us that the Earth can't be as old as they say it is. And as a creationist, I look at it and go, well, 62 million years, is that a problem for me? No, it's not, because there was this thing called the flood, and there was a lot of rock and sand and sediments added to the Earth's oceans. Well, actually, the salt, all the sediments from leveling the planet would have put a lot of salt into the Earth's oceans, wouldn't it? And then as that water came back out, it would have left that behind. Okay, also, if you'll remember, on the third day when God called the waters to gather together in one place and let the dry land appear, and that water came off of the original landmass, off of Rodinia, there'd have been a lot of erosion that day too, wouldn't there? A lot of erosion, a lot of sediments going into the Earth's oceans. So that would be why we could explain easily what would, at the rate it's going now, take 62 million years. But at what was going on, it wouldn't take that near at all, because these were traumatic world global things happening, right, that would have added a lot of sediments into the Earth's oceans. Anyway, so just wanted to deal with that. This is showing you that actually if you looked at the sediments in the ocean themselves, the Earth's oceans can't be as old as they say, because the sediments that are settling to the ocean floors aren't enough to account for billions of years like they want us to believe. And so it goes right along with the salt. Let's go to page 1, is that a 30? Nope. 116, 5.5. Suppose you analyze the salinity of 3 samples of ocean water. 1 was taken from deep in the ocean, 1 was taken from near the surface, and 1 was taken from a place near where a large river emptied into the ocean. If the salinities of these samples were 37 grams per kilogram, 25 grams per kilogram, or 35 grams per kilogram, which one was taken near the river? Which one?
25.
Right, the lowest salinity, because you'd have all that water influxing in there. Thank you. And 5.6, if a lake were completely isolated from a river and stream so that the only way to get rid of water was by evaporation, would it most likely be a freshwater or a saltwater source? Salt water. If the only way the water can leave a source is through evaporation, it's going to be a salt source, because the salt is just going to keep being concentrated in it. And that's the case with the Great Salt Lake in Utah, with the Dead Sea, et cetera, et cetera. Okay? So we see that in places. Now we get to glaciers and icebergs. They look a little white over the top, but when the sun hits them, can you see the blue in here?
Yeah.
It's the color of her shirt. I was shocked at how blue they were. Yes, thank you for that. It's like we coordinated or something. Anyway, they are very blue. You can kind of look in here and see the blue in places, can't you? Okay. Now, glaciers are not from sea ice, and that was this experiment. Okay. So, remember I froze the salt water, and then I took the ice out and I rinsed the ice. And is this going to be salty or fresh water? Because this would be the same thing as sea ice. Will it be salty or fresh? You guys don't know. Well, I'm going to be the guinea pig. Does anybody else want to taste it? I have one more cup. You want to taste it, Bug? Bug just tastes it. Oh, he spit it back out. Okay, let's. Very salty, isn't it, Bug? What we saw there, especially Bug and I, it's very salty. So we know that sea ice does not come from evaporation, condensation, and precipitation, because then it would be fresh water, wouldn't it? Sea ice, actually, he tells us there, is a process where when the salt water freezes, and that rarely happens because the salt, as you saw with your ice cube, when the salt interacts with the water, it lowers the freezing point on the water, and therefore the water, it just ate right through it, didn't it? And that's why they salt the roads up north when it snows, because it lowers the freezing point so that it melts. And the water, the ice and stuff melts. And then it ruins your car. But we won't go there. That's a whole nother story. But the point is that it gets the ice off of the road and the snow off of the road, because it lowers that freezing point of water, because salt water is lower. Now, applying that here, what we see is that the water would freeze with pockets of salt water in it. And that's what Bug and I just tasted, is that it has these pockets of what are called brine, which is concentrated salt water, and it was nasty salty, wasn't it? And so when we rinsed it off, we just had the sea ice, and we let that melt, and it tasted very salty, because sea ice actually is water with little pockets of salt water, brine, frozen in it. So when you melt it, it's extremely salty. Okay, and we also saw that the salt burrowed through our ice cube, which is what we were supposed to see. Yay! On page 118, please. So we said that glaciers and icebergs were the largest freshwater source on the planet, which means they don't come from sea ice, do they? No, we know that now because we know that sea ice is salty. So where do glaciers and icebergs and glaciers come from? What process in the hydrologic cycle do glaciers come from? Precipitation, snow. That's right, precipitation. There's snow on a mountain or someplace where it's cold enough that it doesn't melt every summer. And when it's someplace, so usually it's mountains because they're high altitude, and so it snows on them over time, doesn't melt during the summer. And when that finally gets heavy enough, and the book called it firn, so that's a dense icy patch of old snow, but when it gets heavy enough, then it starts to move down the mountain and eventually will get to the water. Now, ice floats, so it will basically float, but glaciers can be so big and so heavy that they will actually dig into the ground very deeply before, because this is I personally define glaciers as a river of ice. And these rivers can be big enough that you can hide 10-story buildings in these cracks. Just to give you some scale, okay? I've been near some glaciers in Alaska, and they are, you keep walking and walking and walking thinking, well, I thought it was closer. And you keep walking and walking and walking, and it's huge. So when you finally get to it, it was way back there. You know what I'm saying? Because they are huge. And they literally told us on the tour that you can hide a 10-story building in these cracks. They're very dangerous to try to go across them because you just disappear into these cracks if you're one of these people that wants to walk on them. You have to really know what you're doing and be with people that really know what they're doing if you're going to do that.
My grandpa knows someone who actually died in one of those cracks.
That's my point. Thank you. It's very, very dangerous. Okay, and these can be so heavy that when they go down the mountain, they will literally dig deep crevices into the ground before they start leveling out and going towards the ocean. And then when the glacier melts back to that point, those are called glacial lakes. And glacial lakes are known as bottomless lakes because they're thousands of feet deep. And because these glaciers are just so heavy that they'll just literally dig until they hit bedrock and then start moving towards the ocean. Once they get to the ocean, then they will float because ice floats on top of water. And eventually pieces will break off. And when the pieces break off, it's called calving, like a cow giving birth to a baby cow. Okay, calving. Same word. And actually, if you live there, they have all sorts of different words for the different sizes. If it's a little piece, it's got one word, and if it's a bigger piece, it's got another word. And I just never felt the need to learn that because I don't live there, and I just can't relate at all. To me, they're all icebergs, and it's all calving. Okay, they're little icebergs and big icebergs, Anyway, that's salting the roads. Okay, that's the process of calving, and I wanted you to actually see that. Nope. Well, we may not have time anyway. Oh, that's Matanuska Glacier. That's the one that I walked out to see. And it's an inland glacier, and that's actually the water that comes off of that glacier is where they grow all the produce for Alaska. Alaska is amazing if you ever get the chance to go there. That's also Matanuska Glacier. And we don't have time to go into it, but it is, like I said, you keep walking and walking and walking, and it's huge. So it seems like it never gets there. And this is the one you can hide 10-story buildings in. Don't start packing yet. We have 4 minutes, and until that 4 minutes is up, you're mine. So keep your books out. Okay. Let's see. These are the cracks. So like Grant said, it was Alden said it, that you can die in these very easily, and they're covered. So when you're walking on them, literally, you don't see them, and you can just fall in. So it's very important to be tied to people. You can go out there and see glaciers from the boat because they've moved back so far. They've receded since the Ice Age so far that there's waterways in between. And that is the case with the glacier that's in Portage Glacier in Anchorage. They built a visitor center, and now you have to take a boat back to where it is because it's receding. And that's because these things are from the Ice Age, a lot of these. They're not growing. Now, where we do see glaciers growing is in Antarctica. And Antarctica is covered with a basically 2-mile deep glacier. And then as it goes towards the edges, it actually makes ice shelves. And he told us here that this particular ice shelf was actually the size of the state of Texas, just to give you some scale. Yeah, that's a big ice shelf, isn't it? And that just gives you that it's the size of the country of France. So this is a rather large ice shelf. But you got to realize that's 5 million cubic miles of ice. Yeah, it's a lot of ice down there. And then I think about, oh, this gives you some scale too. Do you see the helicopter to give you an idea of the size of the Ross ice shelf? That's a real picture. That's huge. It's like cliffs if you're near it. Well, there you go. This is the Ross ice shelf. Those people are crazy. Okay, that's all I got to say. Anyway, I'm not going to make you watch that, but it shows calving. This is an iceberg, and remember, the vast majority of the iceberg is under the water. That was what I wanted to show you last week. Okay, that's an actual photograph and giving you scale. So the vast majority of the iceberg is underwater, and that's why ships can come on them and hit them and, just be unaware because you can't see what's underneath them. Yes, like Titanic, exactly. Okay. We are... Where did you read to?
120.
Oh, good. Let's just stop here. Okay? You good? Have a blessed day.